Determine with proof all positive integers k such that this expression here is an integer for every positive integer n. So let's try experimenting with some small cases of n. So we can try out n equals 1, but we end up getting 1/2 times the sum ends up being 1 choose 0 to the k plus 1 choose 1 to the k, which is always just 1/2 times 1 plus 1, which is 1. So n plus 1 doesn't tell us anything at all. So what about n equals 2? So we have n equals 2 here. Then we have 1/3 times 2 choose 0 to the k plus 2 choose 1 to the k plus 2 choose 2 to the k. And then if we evaluate this, we end up getting 1/3 times then 1 to the k, that's just 1. 2 to the k, that's 2 to the k. That's an interesting case. Maybe that can help us somehow. And then plus 1 again. So we have 2 to the k plus 2 over 3. And this is an integer. So therefore, 2 to the k plus 2 is divisible by 3. And this means that values like k equals 1 do not work because 2 plus 2 over 3 is not an integer. But even values of k do work because 2 to the k is equivalent to 1 mod 3. So 2 to the k plus 2 is equivalent to 0 mod 3. But if k is odd, then this just becomes a 2 and that becomes a 1, so that doesn't work. Therefore, k must be even. So now we know that k must be even, so let's test out other values of n to see if this is a sufficient condition. So if n equals 3, then we must have 1/4 times, I'll just write out the binomial coefficients, their final form, so it's 1 plus 3 to the k plus 3 to the k plus 1 is equal to 3 to the k plus 1 over 2, and that's clearly a positive integer. So n equals 3 tells us nothing. So now what about n equals 4? Then we have 1 over 4 plus 1 times, again, 1 plus 4 to the k plus 6 to the k plus 4 to the k plus 1 is equal to 1 plus 4 to the k plus 6 to the k plus 4 to the k plus 1 all over 5. And as we did whenever n equals 2, we can try to analyze this using modular arithmetic and reduce these guys modulo 5, and that will make our analysis simpler. Doing so gives us 1 plus negative 1 to the k plus 1 to the k plus negative 1 to the k plus 1. And we want this to be equivalent to 0 mod 5. And when we simplify this further, we get 2 times negative 1 to the k is equivalent to 2 mod 5. So negative 1 to the k is equivalent to 1 mod 5. And this happens precisely when k is even. So n equals 4 doesn't give us anything new again. So it seems like k even is the answer based on looking at small cases. And furthermore, whenever we have k is even, when we have 1, 4, 6, 4, 1, for example, all of them are just equal to 1. So that should do it, right? Well, we should try out some more values of n just to be safe. So let's try out the value n equals 8, because we could get there in a contest, and actually this is where things start to fall apart. Because whenever we do this, we have 1 over 9 times then 1 plus 8 to the k plus 8 choose 2 is 28 to the k. Then 8 choose 3 is 56. 8 choose 4 is 70. And then you just go backwards. And this must be an integer. And whenever k is even, then we get all of this over 9. And then evaluating it gives 1 plus 1. So far, so good. And then another one, again, it's good. But now we run into a problem because now we hit 56. And 56 modulo 9 is 2. So that becomes an issue. So we have 2 to the k plus, and then this one here, it is negative 2 to the k. So that's 2 to the k as well. Similarly, this one is 2 to the k, and then we go back to 1. And what we find here is that we have a bunch of chunks here, and then this just becomes, whenever we group the chunks together, we get 3 times 1 plus 2 to the k plus 1 over 9, which is 1 plus 2 to the k plus 1 over 3. And we already dealt with that case, and that means that k is even. And that k even works whenever n equals 8. So maybe we could try rigorizing this chunking idea. Meaning we want to figure out how these chunks are created in the first place. So we want to figure out a convenient way of writing n choose I. So we have, by definition, n choose I is equal to n factorial over I factorial times n minus I factorial. But there's an easier way to compute it, as you probably know. It's just like n times n minus 1 times n minus 2 all the way to n minus I plus 1 all over I factorial. And if we want to continue to the next chunk, then we get n choose I plus 1 is equal to then n times n minus 1 times n minus 2 all the way to n minus I plus 1 over, actually this becomes n minus I, and then we have it all over I plus 1 factorial. And notice it's just this expression here, so it's n choose k, but we multiply by I plus 1 and then n minus I. So this motivates us to write as follows. So n choose I is equal to n plus, or n over 1 times n minus 1 over 2 times n minus 2 over 3 all the way to n minus I plus 1 over I, where the sum of the numbers in each fraction is n plus 1. And you know what? Let's go ahead and replace n with n minus 1 because it will make computation simpler because we not want to have to deal with n plus 1. So to change it up, we want this sum here to be an integer for all even k. And here this becomes n minus 1 choose I, I'll cross that out, is equal to n minus 1 over 1 times n minus 2 over 2 times n minus 3 over 3, and so on and so forth. Now let's take this modulo n. So this first term here, we have that it's n minus 1, so that's just negative 1. So that's equivalent to negative 1 times, then we have an n minus 2 over 2 term here. So that's basically n over 2 minus 1. And we can take fractions here if we're working modular arithmetic because we can take modular inverses. And we have to be careful about that because fractions in modular arithmetic do not necessarily exist. They only exist whenever the base of the fraction is relatively prime to n. So if n is even, then we run into an issue here. And that's basically where a new chunk begins. Because we end up getting like something different. And then if n is not divisible by 3, then this becomes minus 1 again. So that's negative 1. So when we take it to the power of an even exponent k, we start with 1, then this different number, and then another different number. So that creates this chunk idea. However, if n is divisible by 3 as well, then things become weird because we get another different number, and this makes the chunking idea very hard. So what if we just consider each prime factor separately? That is, we write in this expression n equals p1 to the e1 times p2 to the e2 times all the way to pm to the em. And in this expression, we show that 1 over p1 to pl to the el for l between 1 and m, the sum from I equals 0 to n minus 1 of n minus 1 choose I to the k is in the set of integers. And this will finish by the Chinese remainder theorem. All right, so now we can easily tame these denominators because we only have to deal with them whenever they are divisible by p, l. And in order to make this more concrete, we write this as the product from j equals 1 to I of n minus j over j. And then we should exponentiate both sides to the power of k is equal to the product of j equals 1 to I of n minus j over j to the power of k. And now we want to figure out what this is mod pl to the el. Then if j is not divisible by p, so if pl does not divide j, then j has a modular inverse modulo this number here, which means that since n is divisible by that number, this just evaluates to negative 1 to the k, which is just equivalent to 1. So therefore, these pl not dividing j do not contribute anything. And we only see numbers like this every p terms, numbers where pl is divisible by, where pl divides j. We only see those ones every pl terms, which explains the chunking idea right away. So the real issue arises whenever pl divides j, but then we can simplify this fraction because we get n over pl minus j over pl over j over pl. And that explains why we got our old binomial coefficients, because n minus 1 choose I to the k is equivalent to, then we reindex it in terms of multiples of p is equal to 1, and then we go all the way to floor I over p because that goes to the largest multiple of p right below I. Then it is n over pl minus j prime over j prime to the k, which is just n over pl minus 1 choose I over pl to the k modulo pl to the el. And now we have our chunking idea. So we can go ahead and write it as follows. So our final sum modulo pl to the el is n over pl minus 1 choose 0 to the k a bunch of times. And then we have a few more numbers. And then we just repeat this for every single number, or every single possible value of this denominator. And there are p of these, and then p of these. So our result is the sum of from I equals 0 to n minus 1 of n minus 1 choose I to the k. It's equivalent to the sum from I equals 0 to n minus 1 times n over pl minus 1 choose I to the k times p numbers per chunk, modulo pl to the el. And look, now we have to show that this here is divisible by pl to the el minus 1, but now we reduce this value of n, and the exponent of pl and n is just e to the l minus 1. So this means that we can induct on the exponent of PL in n, and just continue decreasing each exponent until there's none more. So that means that the sum here, by repeating this process, is equivalent to 0 mod PL to the EL. And we repeat this for all of the L, and this means that 1 over the sum, this is an integer. And this proves that all even k work. Since all odd k are ruled out by n equals 2, the answer is all even positive integers. And this is the answer. So thank you so much for watching this video. Please subscribe if you'd like to see more.